hands because in my end, it's also the whole slideshow only. So maybe I'll just really talk. Okay.
It's okay.
All right. Good morning. So this is condensation reactions. Once again, I'm Assistant Professor Melfei Bungihan from the University of Santo Tomas. When we say condensation reactions, it's actually the merge of two larger molecules removing very small molecules, like, for example, removal of water or methanol or ethanol, small molecules, to make new carbon-carbon compounds. So they condense, okay? They come together. And I will be discussing condensation reactions between carbonyl compounds, this two carbonyl compounds. So when we say carbonyl compounds, these are our aldehydes and ketones. And so in this reaction, enolates and enols would react with other carbonyl compounds to form new CC bonds. So just like you see here, an enolate is um, it is called a nucleophile, and an electrophile is your enol. So why enol and why enolate? Because an enol is there's a double bond and an alcohol, because we know that where your carbonyl is, the double bond from your carbonyl goes to the electrons, because bonds can form lone pairs and lone pairs can form bonds, right? And when this goes into that position, you will form a new bond here, which is double bond. That's why it's called N-ol. So it's a double bond and an alcohol. And this one interchanges because we have what we call the keto-enol tautomerism, right? Now, uh, when your enol tautomerizes, before it does that, an enolate may attack that carbon cation or carbocation. So which becomes the electrophile. So basically, in condensation reactions is just an enolate or an enol reaction or a nucleophile electrophile interaction. And this is possible in the presence of a base which obstructs the acidic proton that is alpha to your carbonyl. Here, that's why you form here lone pairs from where your alpha hydrogen was. In doing so, this enolate attacks your enol, and so the formation of a new carbon-carbon bond shown in red is possible. And after that, this lone pair here will go back to its electrons. This lone pair here will get a proton, no, which was technically removed a while ago. And so it becomes an alcohol. So we form a beta hydroxy carbonyl compound. So basically, all of these aldol condensations is the reaction between an enol and enolate to form an aldehyde and an alcohol. That's why it's called aldol condensation. Okay. So the absence or a presence of a leaving group on this electrophilic carbon determines the structure of the final product. Okay, so whether you have now here a secondary alcohol or a tertiary alcohol depends on what are the groups that are attached to your carbonyl. So aldol reactions, two molecules of an aldehyde or a ketone react with each other in the presence of a base. So you have here your hydroxyl, and it forms a beta hydroxy compound. So here is your new CC bond that is formed. Okay, so it could be an aldehyde, two same aldehydes, or it could be aldehyde and ketone. So that's why we also have what we call the mixed aldol. Okay. So um, the mechanism, of course, this is the stepwise mechanism. Of course, the base could be a sodium hydroxide or any base at all can get the acidic proton, alpha proton from your carbonyl compound, so your aldehyde or your ketone. And then it will give you a resonance stabilized enolate. So this is your enolate. So we have your keto enol tautomers here. So this is resonance stabilized, and there is now what we call a nucleophilic attack. So this enolate is becoming a nucleophile because of the presence of here your electrons here. This becomes electron rich, and so it will go to your to any carbon that is a cation, so electrophilic. So how does this aldehyde becomes electrophilic? That is due to the delocalization of the double bonds into lone pairs towards your oxygen. So this carbon now is their electrophilic carbon. And then the new formation of a CC bond here, uh, after this nucleophilic attack, gives you this intermediate and protonation from your water forms your alcohol. uh, Here, your alcohol. So you now have an alpha beta. So your beta is your hydroxyl group is in the beta position. That's why we call it beta hydroxyaldehyde. Okay, so that is the um, basic of the aldol condensation. So the aldol reaction has irreversible equilibrium. So the position of the equilibrium depends on the base and the carbonyl compound. Of course, the hydroxyl from your sodium hydroxide, for example, is the base typically used in aldol reaction. So although with OH, only as a small amount of enolate is formed. So this is appropriate because starting aldehyde is needed to react with the enolate in the second step of the reaction. So we needed that starting aldehyde. Then all the reactions can be carried out with either aldehydes or ketones. Even if we are saying aldol, it's not just aldehyde. Okay, so sometimes I call it ketol reaction because if it's ketone and alcohol, it's basically the same. The only difference is of course the starting carbonyl compound. So the with the aldehydes, of course, the equilibrium favors the products. But with ketones, there is what we call a reversible reaction. There is a reversal. So it favors the starting materials. So, however, there are ways of driving the equilibrium towards the products, of course. Now, let's look at the nucleophilic addition of enolates. Okay. So, characteristic reaction of this aldehydes and ketones, of course, is we call it nucleophilic addition. Okay, you have discussed so far nucleophilic substitution, electrophilic reactions. We have electrophilic addition, right, in your previous topics. Um, in here, we'll be dealing with nucleophilic addition. Okay, so an older reaction is nucleophilic addition, in which the enolate is your nucleophile because it is the one that is attacking your electrophile. So it is the one which is electron rich. Okay. So the nucleophile, your enolate, goes into your carbonyl. So that's nucleophilic addition. So basically, if you look at nucleophilic addition and aldol reaction, they are the same. So it says aldol reaction is a nucleophilic addition reaction. So let's look at propanol, for example. Looking at carbon, additional carbon at your alpha hydrogen. Okay, propanol. So still your alpha hydrogen is acidic in character. It can be abstracted by a base. And then this is a base attack. No? And then you form now the nucleophile. Okay. So, and it attacks, of course, the carbonyl carbon in the other propanol. And so you form your CC bond, red. And then, of course, you will have here uh, addition of water or protonation of your alkoxide will give you your beta hydroxy. So basically, what you will do here is just recognize where is your alpha and beta carbons. It's where you have the connections. So when you will having the retrosynthesis later, looking at your beta hydroxy aldehyde or ketone, you can split the molecule in half and you will see what are the starting materials, whether they are aldehydes or ketones or both aldehydes or both ketones. Okay. So even if the aldehyde becomes more complex, you have more R groups here after your alpha, you would still mark this alpha carbon as your nucleophile. And you just have to follow placing all those R groups, lengthy R groups next to your alpha carbon, okay? Because that is where you produce your enolate or your nucleophile. Okay, so joining carbons to form aldol products is just basically that way. Okay, look at the alpha carbon of one carbonyl and look at the carbonyl of the other and then connect them. Okay, and then connect all the other groups, the R groups, and so you form your beta hydroxy carbonyl compound. It could be a ketone. If this is an R group here, then this is an R group here. So it is now beta hydroxyketone. Okay? But if it's an aldehyde, then you have your beta hydroxy aldehyde. Okay? Now, how about if we dehydrate the aldol product? Okay, it is possible to do dehydration, removal of the alcohol group, so H and OH to adjacent group from your alpha and beta. You will form an alpha beta unsaturated carbonyl compound. Okay, so in biological systems, this also happens. Okay, the dehydration process, especially in fatty acids, no, to form your alpha beta unsaturated acids. Okay, so here example, we do the aldol. So we have two acetaldehydes. We will form as a product beta hydroxyaldehyde. Now, further, if we dehydrate, that means removal of water, then we form your alpha beta unsaturated carbonyl compound. So for acetophenone, see here, uh, this is your
So,
enolate.
Melfei, your slide
Yes.
not moving, not moving.
Oh,
Uh,
what slide is it, doctor?
this is slide two.
Slide 2? I'm
Yeah.
already in slide 9. My God. I'm
So
sorry.
let's move to the next slide. Can try move to
Uh-huh.
the next. Melfei. Then then uh,
Sorry, I'm
okay.
already here at the, I'm sorry. Maybe
It's okay.
it cannot do the, if I do the, the slideshow, Google Meet cannot. Sorry.
Okay. You just click
Maybe
once you
just,
want to move to the another slide, you just click and then
oh, I'm
okay.
sorry. Wait.
You can proceed. You can proceed.
This
It's okay.
actually this is always our problem with Google Meet. That's why we
Sorry,
are not
because
always using Google Meet.
we prepare the platform for Google Meet.
Uh-huh. Yeah, I think. Oh,
Okay, so now it's 9.
I'm already in slide 9. I'm so sorry.
Okay, it's okay.
Okay. All right. So this is what I'm telling you that although, okay, two aldehydes and ketones, so two aldehydes will form an aldol. So if it's just in slide 2, this one, no, this one. So
Uh,
let me run through again.
just brief for the previous slide 3 until
Yeah.
8. Okay.
Yeah, I think, yeah, okay. So here, the aldol is basically just the reaction between the aldehyde and another aldehyde or ketone and ketone. Okay, so we have here the uh, reaction. This is the totality of the reaction for aldol. So this is the base abstracts your acidic proton, and then it will form an enolate, which is a nucleophile, right? So your nucleophile now attacks the other carbonyl compound, which is your electrophile, because your conjugate, yeah, no, your double bond here goes into your oxygen, the electrons, making your carbon here carbocation. Okay. So your enolate is resonance stabilized because it is can tautomerize into ketoenol, right? And then after that, there's a new CC bond, and then the alkoxide here in your beta position becomes protonated, and then you will form your beta hydroxy aldehyde. So basically, that is for aldol. So the rest of the one that I've been discussing a while ago are this one. Okay, so how the base reacts to form your aldol, and then the how your aldol reaction is called a nucleophilic addition. Basically, the enolate is your nucleophile that forms CC bond here. So the same. So we are saying this is a nucleophilic addition because the nucleophile, your enolate, adds to your carbonyl. And then your alpha carbon, when it's bonded to more R groups, then it doesn't matter. You just have more R groups here at your alpha carbon. But you just think of your alpha position and how it connects to the carbonyl of the other aldehyde or the ketone. Okay, so that you form your CC bond. So now this is where I had been. Now, if we have already an aldol product, which is a beta hydroxy carbonyl compound, dehydration can be done. Okay, so that is removal of water. So remove the adjacent hydrogen and hydroxyl between alpha and beta carbons. So you form your alpha beta unsaturated carbonyl compound. Okay. So it is the same thing when we dehydrate from your ketones. So your ketone here is your alpha carbon. So you have your alpha hydrogen here. Okay. So after that, you will form a bond between this carbon and the carbonyl of the other acetophenol. So this now is having your um, beta hydroxy carbonyl compound, but this is not isolated. It usually undergoes dehydration process. And so you form your alpha beta unsaturated compound. Okay. Excuse me, from your ketone. Now, of course, you see here an isomerism because you have your double bonds. Okay, so you've had your lessons on E and Z isomers. So you can have your formation of easy isomers for your acetophenone if it undergoes aldol condensation. So an aldol reaction is often called aldol condensation because the beta hydroxycarbonyl compound is initially formed, loses the water by dehydration. So the loss of water is what we call the condensation process in organic chemistry. So uh, we also have some other reactions where we have condensation reactions like Dickmann, loss of other smaller molecules like methanol. So small molecules are eliminated during reactions in condensation reactions. Now, when the alpha beta unsaturated carbonyl compound is further conjugated with carbon carbon double bond or a benzene ring, elimination of water is spontaneous. That is why we do not we cannot isolate the beta hydroxy carbonyl compound for the very large molecule. There are benzene rings and there are double bonds present in the molecule. So usually it goes through the product of removal of water. So that is your alpha beta unsaturated carbonyls. So here, the dehydration with a base, no, is just basically the abstraction again of your acidic proton. You know that this is acidic proton because it's between um, carbonyl and the hydroxyl here. So that draws the electrons towards themselves, making this proton easily remove. Okay, so that uh, there will be now what we call your lone pair here that attacks your that delocalizes, attacks your OH, and so removal of this bond between carbon and oxygen. So that is now spontaneous removal of water. Now, uh, this goes through having now your alpha beta unsaturated compound. So it's the mechanism for the dehydration process. Now, we also have what we call the E1CB mechanism. Of course, we know E1, that's elimination reaction. But in E1, of course, we know that uh, there must be a formation of a carbocation. But in the E1CB mechanism for our condensation reaction, we have the reaction of a carbanion. Okay. So E1CB stands for elimination, unimolecular. Okay? So we have the intermediate. It's a carbocation usually for E1, but in here it's a carbanion. And we need a conjugate base. Okay. So that's why E1CB. So it differs from E1 and E2 mechanisms in this case. Now, unlike like the E1, E1CB requires two steps. Okay, two steps. The formation of an intermediate. Okay. Unlike E1 though, the intermediate is here a carbanion, not a carbocation that we have learned before in your E1, E2 mechanisms, E1 mechanisms. Okay. Now, regular alcohols dehydrate only in the presence of acids. They do not dehydrate very much in the presence of an acid, not base, because hydroxide, of course, is a very poor Lebesgue group. Okay, poor Lebesgue group. However, if we have your hydroxy beta to your carbonyl, the loss of water or the removal of the OH from the beta position is stabilized. And so, what stabilizes it is the conjugated system because you have still the carbonyl group there. Okay, so it makes up for poor Lebesgue group characteristics of your hydroxyl. So, the dehydration of the initial beta hydroxycarbonyl compounds drives the equilibrium, favoring the product formation. So take note the mechanism is E1CB. Now, as I was saying a while ago, I'm sorry that you were not, you cannot see the slides. It was not moving. That if you're given a product like your alpha beta unsaturated carbonyl or your beta hydroxy carbonyls, then you could predict actually the starting materials. And this is what we call the retrosynthetic analysis of the aldol products. For example, we have here your beta hydroxy carbon aldehyde and your alpha beta unsaturated ketone here. Now, we can predict what are the starting materials of these two compounds by first locating the alpha and beta carbons. So in letter A, we have here your alpha position, so alpha to your carbonyl, and then beta position. So that is, you mark this already because this is the one that has formed the CC bond. Okay. In B, this is your alpha and this is your beta. And so that is where um, you have your um, new CC bond was formed. So that's the first step. You locate your alpha and beta carbons. So there, then from there, you break the molecule. So once broken, you form, of course, one carbonyl compound and another carbonyl compound. Okay, so of course there are several steps here because from your, you know that the OH was actually coming from your CO, from your carbonyl. That is where your carbocation was. Okay, so here you see now the two starting materials. In the other compound, of course, you break this bond, and so of course there are several steps here because it has undergone dehydration, okay, to become an alpha beta unsaturated ketone. After that, then you can form here the starting materials. You see those cyclohexanones, two molecules. So that is how you can predict what starting material has caused these condensed products. Now, we also have what we call the cross-aldol reactions. You have seen so far reactions of the same type of um, aldehyde or same type of ketone. But what if we have different aldehydes and different ketones that are reacting? We call that cross-aldol reactions, or we can call them mixed aldol reactions. So for example, in acetaldehyde, okay, can form an enolate, right? Acetaldehyde and propanol reacting together. But you know that acetaldehyde forming an enolate can um, mix with itself, okay, can condense with itself. So the acetaldehyde becoming the um, electrophile, you will form this beta hydroxy compound. Now, if it reacts with propanol, you form this beta hydroxy compound. Now, your propanol can also do the same. It can it can aldol, do the aldol condensation with itself or with your acetaldehyde. So you form these products. Okay? So there are four different products that can be produced from mixing these two types of aldehydes, two different aldehydes. So the conclusion here is when two different aldehydes have alpha hydrogens, look, they have both alpha hydrogens, a cross aldol reaction happens. And there are mixtures of products that can be formed. So that's why they're saying cross aldo or mixed aldo are not very synthetically useful. But there are some very good uses of these cross aldol reactions. So these are the two situations wherein cross aldol reactions is very good. So when only one carbonyl component has alpha hydrogens, such cases often lead to the formation of only one product. So it's very specific. So cross aldol is not very useful if you have a lot of alpha hydrogens from both carbonyl compounds. Okay, so here, for example, we only have one alpha hydrogen. The other carbonyl compound has no alpha hydrogen. So only one carbonyl compound can become an enolate. Okay, and it will attack your enol. Okay, and so you will form beta hydroxy aldehyde, which eventually can be dehydrated. Why is it that it can be dehydrated? Because of the presence here of your aromatics, which can drive the process to go through from aldol to beta, alpha beta unsaturated carbonyl. Okay. On the other hand, uh, here, this is your same, right? Okay, but you have here the cinnamaldehyde. No? Okay, another one. No? On the other hand, we have when one carbonyl component has especially acidic alpha hydrogens. When do we have especially acidic alpha hydrogens? When you have a lot of these dicarbonyl compounds and related compounds, okay, which are electron withdrawing groups. So your alpha hydrogen here is very acidic. Okay, they are more readily removed than the other hydrogen atoms. Okay, so these are acidic. So your dicarbonyls here and diesters, you have here your diesters, makes this alpha hydrogen very acidic. Okay, and so it forms the enolate very readily, and it will form an aldol. Okay. Of course, uh, eventually it forms one final product, which is an alpha beta unsaturated carbonyls. From here, carboxyls in this case. Okay. So we have here, in this type of cross-aldol reaction, the initial beta hydroxy compounds always loses the water to form your conjugated products. Okay. Now, how about the presence of active methylene compounds? Okay. So, beta dicarbonyl. So, have your beta diesters, keto ester. We also have your cyano, which is a derivative of your carbonyls, of course. And then we have also one with dinitrile. Okay. So they are called active methylenes because they are more reactive towards base than other carbonyl compounds. So 1,3-dinitriles and this alpha cyano are also active methylene compounds. These are your very active compounds. CH2s. Okay. Very acidic hydrogens that they have. Okay. Now, How about this directed aldol reactions? Why do we call them directed aldol reactions? So it's one that clearly defines which carbonyl compound becomes the nucleophilic enolate and which becomes the electrophilic carbonyl carbon. Okay, so it's has already a pre-selected enolate. Okay, then of course, if one is enolate, the other one is the electrophilic. Okay. So the enolate of one carbonyl component is prepared with lithium, uh, diisopropyl amine. Okay, LDA, lithium isopropylamide. Okay, so the second carbonyl compound is added to this enolate. So both carbonyl components have alpha hydrogens because only one enolate is prepared with LDA. Now, when an unsymmetric ketone is used, LDA selectively forms the less substituted kinetic enolate. And this is how we direct uh, in synthesis, just like what Dr. Noor is doing in her lab, of course. They want to synthesize in such a way that they select already which one would react with the other. Okay. So in that is when we want to direct our aldol reactions and we want this one to be the enolate and the other one is the electrophile, we have to pre-select our starting material. Okay. Now, in this one, periplanone B is actually an extremely active compound produced by cockroaches now, specifically the American cockroach. So, structure was determined using 200 milligrams isolated from more than 75,000 female cockroaches. Okay, so it's only from female cockroaches. So, this is actually directed aldol reaction. So, uh, now, the protonation of your carbonyl, your alpha hydrogen here, with LDA instead of your OH, of course, LDA is your base here, will form your enolate. Now, uh, this is already your enolate, and you can react it with another carbonyl compound, which will act as your electrophile. So in this case, this is your electrophile that forms a CC bond at your enolate. And of course, it will take several steps before you can have this whole periplanone B. So it's just telling you that periplanone B can be started with the aldol condensation first, and then several steps to give you, of course, um, those, your epoxide formation from your double bond, something like that. Okay. Now, we also have what we call the intra molecular aldol condensations. Means in a molecule, you have already your carbonyl compounds. So your carbonyl compounds then will react such a way that you still form new CC bonds, but this time it gives you a cyclic structure as your product. Okay, excuse me. So you can form now five or six membered rings from your diones or your diols. Okay. So the enolate form from one carbonyl is the nucleophile, and the other carbonyl compound is your electrophile. So you just have to choose which one is your enolate, your nucleophile, and which one is your electrophile. But in this example, of course, it's very symmetrical. Okay, so whatever becomes your choice. Okay, So if we redraw this in order for us to have the closer, uh, closer inolate nucleophile electrophile interaction, we redraw this like this. No? And then, of course, abstraction via base, sodium ethoxide, will give you this as your um, uh, oh, you look at your now your alpha carbon, okay, and then your alpha carbon can be this or this. We also have here alpha here and then alpha here. Okay. Now, since you formed now the new CC bond um, here, so where was your formation? Uh, where was the reaction that happened? Okay, so look at this carbons here. One, two, three, the red one, four, five, six. So 1, 2, 3, 4, 5, 6. So if you have split, you know that this is where you have your COH. Okay, COH. So that means what actually reacted is this one bonding to your this one bonding. I don't know if you are seeing my um, pointer. It's bonding to the original carbonyl here so that you form your five-membered ring. Then dehydration removes the uh, OH and forms your alpha beta unsaturated ketone. Okay, so looking at the mechanism, of course, there. So your base, your sodium ethoxide abstracts the alpha hydrogen. Okay, this is the most accessible one. Okay, and thus becomes your enolate, which attacks your carbonyl. It redrawing it gives the proximity between the enolate and the electrophile. And after that, you form now your five-membered ring. So there's closure, and then you form your beta hydroxy compound, and then after that is dehydration to form this. Okay. So this one is via the E1CB mechanism, the loss of OH, HOH or water. Now, um, use of cross-aldol, we can also have this cross-aldol in intermolecular reaction. Okay, so because you see here, the compound is no longer very symmetrical. So the identity of your ketone at the right and your ketone at the left are different. So it becomes a cross-aldol reaction. So basically, still the same. No? You can have choices of your alpha hydrogens, right? So alpha hydrogen, the other one is also alpha hydrogen, HA and HB. Now, if you make an enolate out of HA, you form intermediate A, and so you form this product. Okay? This product, the five-membered ring, alpha beta unsaturated ketone. Now, if abstraction of the base loses your HB, you will form an enolate B. Okay? and and so that one will attack the carbonyl the other side, and you will form a three-membered ring, which basically, if you look at um, the first product and the uh, second product is very much strained, no? That's why you see here it reverses back. Okay, it does not form. Okay, the three-membered ring does not form. So the three-membered ring has much higher energy than that of the five-membered ring. That is why we can isolate this five-membered ring, but not the three-membered ring product. Now, if we have larger molecules, of course, okay, just like this, heptane 2,6-dione, then we can have six-membered ring. Okay, so basically the same process, and then you form the CC bond, but this time it is a larger ring. Now, in the synthesis of progesterone, okay, progesterone is a female hormone. Okay, using the intramolecular aldol reactions, we have here uh, the formation. You look at the moiety which had undergone, of course, your condensation. Okay, so this is one example of having the intramolecular aldol reaction. So you see here from this bond, okay, from this bond, you know that it has this, okay, this original formation. Um, no, original formation from here. Ozonation, of course, ozonation, ozonolysis will give you from a double bond from an alkene, it forms a dione or aldehyde and ketone formation, right, in ozone, depending on the R groups here in your double bond. So, uh, this ozonolysis, okay, cleaves this to form your dione. And your dione can form your alpha, beta, unsaturated ketone via the aldol reaction. That's why you see here the base, then the water, and then removal of your HOH to form your alpha, beta, unsaturated compound. That part of your progesterone is actually the one where aldol reaction was involved. Okay. Now, let's go to Claisen reaction, which is uh, named reaction. It was introduced by Claisen. Is basically the uh, the aldol condensation, also condensation, but in here we have esters. Okay, instead of aldehydes and ketones. So two molecules of an ester react with each other in the presence of an alkoxide base, okay, like your sodium ethoxide, to form a beta keto ester. So we have your keto ester. So unlike the aldol, which is base catalyzed, a full equivalent of base is needed to deprotonate your beta keto ester that is formed in the Claisen reaction. Okay. So, for example here, your ethyl acetate via Claisen reaction, you still form the new CC bond, but you have here a keto at the beta position. So, since esters have a leaving group, now we have here your part of the alcohol moiety. Uh, It occurs, the loss of the leaving group occurs to form the product of substitution, not addition. Okay. So it becomes substitution. So let's see. So in Claisen reaction, the first part is formation of the beta keto ester. So initially, base of course removes the alpha proton. And then we have your enolate formation. And then we have the nucleophilic attack. So nucleophilic attack here will give you uh, this formation of CC bond, but take note here that there is a leaving group in an ester here. Okay, so there is an elimination of the alcohol moiety of the ester. How does it become eliminated? When the lone pairs in your alcohol goes back to its carbon, then you form your beta keto ester. Okay, now part 2, the second part after this beta keto ester is deprotonation and protonation. So deprotonation, you know that your dicarbonyls, uh, the methylene carbon is active, very active. So this proton here is easily abstracted by a base, and so it forms a new resonance stabilized enolate. Okay, this enolate then becomes protonated, okay, to form your beta keto ester. Okay, so there is stabilization of your final product via deprotonation and protonation. So in here, of course, you need um, strong acid to protonate your um, resonance stabilized enolate, and so you form your beta keto ester. So that's Claisen. Okay, so what did we remove? Actually, what we remove is the alcohol moiety. So I told you a while ago that condensation is removal of small molecules like water, alcohols. Okay, so the alcohol moiety of your ester, this ethanol. Okay, ethanol here in this case was uh, the one that is removed in the condensation process in Claisen. Okay, so it's basically this slide is the same as what I have discussed a while ago. Now we also have cross-Claisen reaction. Of course, it's possible to react to different esters. Okay, so like your ethyl benzoate and ethyl acetate. So this is cross-Claisen. Okay, now in this case, you have to look at the ester with an alpha hydrogen, and that will become your enolate. Okay, and then that enolate will attack your carbonyl in the other ester to form your new CC bond. You still have your beta keto ester as the product. Okay? So between a ketone and an ester, it's also possible, right? Because of the presence of an alpha hydrogen here. Okay. So your enolate is your cyclohexanone, and then it react with your ethyl acetate to form your dicarbonyl compound. Right? Now, forming beta dicarbonyl compounds uh, can be done with ethyl chloroformate or diethyl carbonate. Okay, so, so your ethyl chloroformate still contains your C double bond O, becomes your carbocation, your electrophile. Also here, diethyl carbonates uh, very complex in such a way that it's full of oxygens or electron withdrawing groups, making your carbon here, your carbocation, a good electrophile. So it's also possible to form uh, beta dicarbonyl compounds this way. Okay, and you see, you just have to look at uh, the groups that are being removed. You can the living group here in your ethyl chloroformate is of course your chloride, no, your chlorine, and the other one of course is your ethanol. See, these are small molecules. Okay, so ethanol or HCl is removed in these two compounds, right? So beta keto esters, okay, from um, yeah, elimination process. So this is basically the way by which we prepare a lot of different beta keto esters. So easy access, useful in acetoacetic ester synthesis. Okay. Now, we also have what we call the Dickman reaction. So I understand that uh, it's called Robinson annulation and Claisen before, but I would like to discuss also Dickman reaction because basically these are almost the same. Okay, so I might as well cover it. Okay, but Dickman reaction is an intramolecular Claisen reaction. Okay, so it's basically Claisen, but it is intramolecular. So in here, again, we form what we call the rings. Okay, the only difference here is, of course, we have your beta keto ester. Okay, so that's a Dickman reaction. So two types of diesters will give yields of your cyclic products. So we have here your 1,6 diester. If you redraw it in such a way that your alpha hydrogen is in proximity, alpha carbon is in proximity to your carbonyl. Okay, here. So you form your beta keto ester. For 1,6 diesters, of course, you form a 5-membered ring. For 1,7 diesters, you form a 6-membered ring. Okay. If you have 1,8 diester, of course, you will have your 7-membered ring. So the mechanism, of course, is uh, look at where you will remove your alpha hydrogen. Okay. So to form your enolate. And then, first, once the enolate is formed, it will look at your um, electrophile. And then, of course, there is what we call here a tetrahedral intermediate. Okay. From and removal of the leaving group to retain your carbonyl group. We call it the elimination process. And then protonation, the protonation to stabilize now your beta keto diester. Okay. So, yan. Uh, Under basic reaction conditions, the proton between the two carbonyl is removed with base to form the enolate, which is protonated with an acid to reform your beta keto ester. So it's still important to have your 4 and 5, which will stabilize your final product. Okay. Now, aside from Dickman reaction, we also have the Michael reaction. Okay. Michael reaction involves two carbonyl components. The enolate of one carbonyl compound with an alpha beta unsaturated carbonyl compound. So you see, it's not just a carbonyl compound, your electrophile, but an alpha beta unsaturated carbonyl compound. There's additional conjugation here in Michael addition. Okay. So in this case, there will be, of course, choices of of attack, right? Because of resonance that can happen in your alpha beta unsaturated carbonyl compound. So you form uh, the carbocation once you delocalize the electron rich part of the molecule. And so you will have hybrid electrophilic sites. And in that case, your enolate will have to choose which one is the better electrophilic site. Okay, so these resonance structures from your alpha beta and saturated structure will give you compound will give you these hybrid electrophilic sites that will be attacked by your enolate. So we have what we call the Michael acceptors. Okay, so the alpha beta unsaturated carbonyl is called your Michael acceptor. Okay, um, in the first one, your Michael acceptor uh, is this, no? Acyclic. Then, of course, your dicarbonyl contains your alpha hydrogen here. This becomes your enolate. And removal by a base of this proton will give you this enolate, and then the CC bond is formed here at the beta position. Okay. This, this case. So this is now your um, condensation product. Okay. Now, if your Michael acceptor is this one, okay, your cyclic uh, alpha beta unsaturated cyclohexanone, same. No, we have a different, of course, dicarbonyl compound. You will form this CC bond. You just have to look at where will be the formation of your CC bond. So it is at the beta position which was which there is a formation of a bond and not at the carbonyl. No? Not at the carbonyl. So in Claisen, in Dickman, we are looking at the carbonyl as your electrophile. But in this case, your Michael acceptor, your electrophile is actually your beta carbon. That is why your new CC bond is um, not formed with your carbonyl. So you don't have what we call the alpha beta the unsaturated carbonyl or your beta hydroxycarbonyl. But you retain your carbonyl, but the new CC bond is between, okay, your enolate and the original beta unsaturated carbon. So that's for Michael addition, Michael reaction. Okay, so there. This is the detail of what I've discussed so far. And so in Michael reaction, we call it the 1,4 addition product. Okay, so it's a 1,4 addition product because we added the enolate at the 1,4 position of your electrophilic hybrid. So here, in this case, you have here the 1,5 dicarbonyl compound as the product. So if we have a beta keto ester, it can be hydrolyzed and decarboxylated now by heating. No, you can remove this from the Michael product. When you heat it, we can remove this becomes a living group, and so we remove carbon, this COO here. So you form this product. Now, where do we use this Michael reaction? First, synthesis of steroid estrone. Okay. So looking at the molecule now, the estrone, where was the reaction that happened? Where was the Michael reaction that had happened? Okay. So of course, there is look. You have to locate where is the addition of carbon-carbon bond, the carbon-carbon addition. Here, this moiety and the other moiety. So this is where you had the um, condensation reaction that happened. Okay. That was Michael addition. Right, so I hope you are following me now. We now have the last, I think this is the last, and the Robinson's annulation. Okay. Um, Robinson's annulation is actually also a ring-forming reaction. Okay, it combines the Michael reaction and the intramolecular aldol reaction. Okay, so Michael plus aldol, and then you combine them, and that is what we call the Robinson annulation. The starting materials are, of course, alpha, beta, unsaturated carbonyl, which is from your Michael reaction. And an inolate could be an aldehyde or a ketone. Okay. So we need here a base, and then you form two new sigma bonds and one new pi bond. So those are the ones that are formed in Robinson's annulation. So let's look at the details for Robinson annulation. So again, it's a combination of Michael and aldol, and it's intramolecular. It's ring formation. So the Robinson annulation forms a new six-membered ring. So you see here your six-membered rings. Okay. And of course, it will have two new bonds. So sigma bond and one pi bond. Okay, sigma bond and one pi bond. And your product contains, of course, your alpha, beta, unsaturated ketone. So to generate, of course, the inolate component of the Robinson's annulation, of course, we need your hydroxyl in water or your alkoxide in ethanol, no? Just as what we are doing in Claisen or aldol condensation. In aldol condensation. Yeah, sorry. And of course, the details now for Robinson annulation, we have this part one, of course, is Michael addition. Okay. So in your Michael addition, you form your uh, inolate plus your alpha beta unsaturated ketone. Okay, so forming your uh, new CC bond. Okay, now your new CC bond here is sigma, a sigma bond. Okay. Then you form, of course, from this reaction, you form your dicarbonyl compound. Okay, 1,5-dicarbonyl compound. And since you have your 1,5-dicarbonyl compound, your dicarbonyls now can form intramolecular aldol reaction. So again, you needed a base to abstract the proton alpha hydrogen to form your inolate, which now attacks your carbonyl closest to it, no? To form now the ring. Okay? And forming the ring will give you an alkoxide, which, when protonated, will give you a beta hydroxy carbonyl compound, which you know that your beta hydroxyl compound, okay, will dehydrate eventually to form your double bond. Okay, so that you have now a pi bond that is formed after dehydration of your beta hydroxycarbonyl compound. So there, yeah, the dehydration process will give you the new carbon-carbon bond that has become a pi bond. Okay. So this dehydration again happened via your E1CB mechanism. Okay, the loss of proton from an enolate and elimination of OH, because we just don't eliminate OH as is because it's not a good living group. But in this case, E1CB mechanism is happening. Okay. Now, yeah, to draw the products of Robinson annulation without writing out the entire mechanism each time, you just need to look into what were the positions that were reacting together. Okay, place the alpha carbon of the carbonyl compound that becomes the enolate. Okay, so of course, your carbonyl compound becomes your enolate, because your alpha beta unsaturated ketone, of course, is your electrophile based on Michael's. Okay, so you have to join these two together, and then join the appropriate carbons together, as shown. No? So this one is also your alpha hydrogen that is reacting with your carbonyl in your, I should say, aldol. Okay, intramolecular aldol. After joining the first alpha beta, then you can join the second alpha beta, and then the hydration will give you the pi bond. So it's always ends up in the same position. That's why Robinson's annulation is the formation of a six-membered ring, new six-membered ring. So even if your enolate here, your carbonyl is not a ring type, no, then you just don't worry about it. You just put in all the R groups that are attached to the specific reacting sites. Okay, so whether it's very simple compound aldehyde or very complex, you just have to look at which ones are reacting. They are just the most important ones. So without always writing out the entire mechanism at the same time, uh, when your professor would ask you, um, you try to look into the starting material, then you know where the positions that had been joined together and how you split them up on those positions. Okay, yeah. So how to synthesize compound using the Robinson's annulation. So here, this one is more complex as you see, but if you know where to locate the positions, then you can never go wrong into the mechanism, of course. Okay? So, what starting materials are needed to synthesize this compound using Robinson's annulation? Of course, you look at this portion of the molecule where you have your alpha, beta, and saturated ketone, and then you know that that is where you have this synthesis now, and then you will know where had been your CO and where had been your the initial carbonyls, of course. Okay, so break. You break now your cyclohexanone. You break here, you break there, the bonds. Then you have your alpha beta unsaturated ketone, and you have your um, enolate, source of your enolate, your carbonyl compound. Okay. And yeah, I think, uh, yeah, that is all for, I think I have gone too fast, doctor. I'm sorry.
Okay,
Did
thank
I
you.
go too fast?
Thank you so much, Dr. Melfei. So actually you on time, 11. 11.
11:30. Yeah. Yeah, 11:30.
Another four minutes, but it's okay because I'm doing this session actually from 10 o'clock until 12 p.m. So we have
Oh,
around 30 minutes. If any of you have
and
Q&A
questions?
questions, you can ask directly to Dr. Melfei. Any of
Oh,
you?
you have a lot of students.
So actually now we have 61 students.
Oh,
Quite a lot, but I need some question from student.
mhm.
We have one question in chat box. Okay, doctor, I want to ask, in Claisen condensation, why is it necessary to use a base that match the ester alkoxy group? What would happen if we use a different base?
Ah, wait.
I, I,
I
I
thought.
repeat again.
Okay,
Okay,
I read.
okay. In Claisen condensation, why is it necessary to use a base that same with the ester alkoxy group? And what would happen if we use a different base? From Nur Fatihah
Ah,
Abdul.
yeah. Why is it necessary to use a base that matches the esters alkoxy group? What will happen if we use a different base? The alkoxy that matches the esters alkoxy group. Ah, of course, we wanted the base that is able to abstract, no, abstract the proton. If it's not strong enough, then we cannot remove, no, we cannot remove the proton, and so there will be, if there's no removal of the acidic proton, then there will be no movement of these electrons, and so there is no removal of the leaving groove. So we need to really look at the base, which is strong enough to remove the acidic hydrogen, of course. And what's that? The base that matches the esters. Ah, for the alkoxy leaving group, no? The alkoxy leaving group, of course. Alkoxy leaving groups are good leaving groups, no? Um, of the esters. No? So that is why we just use actually simple bases. They are not very strong enough. These strong bases. We use strong bases if it is hard to remove these the groups that we wanted to remove, like your protons are not acidic enough, or the living groups cannot live enough. Then that is the time that um, you have to adjust the identity of your base. But as you have seen, there are these are not very strong bases, and they can still really remove the the protons. Now,
Okay.
there's another.
Yes, another question to doctor. How does the choice of base affect the enolate formation and ultimately the efficiency and outcome of the dehydrogen step in aldol condensation? This question from
Uh-huh,
aldol condensation, Dr. Melfei. From
uh-huh,
Nurdian. Okay, thank you,
uh-uh.
Dian.
Okay, okay. Thank you, Nur. Yeah. The inlet formation is the very important step for us to have our condensation process. Um, because if our base, as I have said, is not strong enough to remove the acidic proton, then the inolate is not formed. There will be no lone pair there to form our inolates. So that is why if our proton alpha hydrogen is not acidic enough, because when we say acidic hydrogen, this is a hydrogen that can be easily removed. However, there are cases that the hydrogen is not easily removed, that there are no other groups that will make it more acidic. Then we needed a stronger base. It's just for the abstraction of the alpha hydrogen to form your inolate. Because if you are not able, if you're not successful to form your inolate, then there's no condensation that can happen. Okay, so if just like your ethoxide, for example, or water alone, no? Water alone cannot remove, no? The water can act as an acid or a base. If water alone is acting as a base, and it's not a hydroxyl or alkoxide that can abstract this hydrogen, no formation of inolate happens. And so with that, no condensation happens. you cannot form your nucleophile if you don't have strong enough base to abstract your alpha hydrogen. Okay, so it's very important that uh, your base can abstract your alpha hydrogen. Uh,
Okay. For the next question, thank you for Nudiana. So next question from Nur Ayu Shafika Zamri. Doctor, can I ask why does the Dickman, this is topic from Dickman, Dr. Melfei, typically only form
Sigmund.
or six membrane?
Uh-huh. Yeah, it forms six-membered and five-membered rings. Yeah, wait lang. Yeah. Um, Now, the Dickman reaction can also happen for larger or smaller rings. Problem is, it's a reversible reaction, and so what happens is, um, because if you can condense, you can also split, right? But if you are forming, for example, larger rings, the problem with that is it's not very stable. And if you form smaller rings, it's also not stable. So stability is very important. You may form them, but they are not kinetically or thermodynamically stable enough to form the product. It goes back. It is becoming reversible. So six-membered rings and five-membered rings will uh, are more stable no, than other rings. You can form via that reaction. However, you will not be synthetically successful because of this thermodynamic and kinetic considerations. Okay, so that's why this five and six membered rings are preferred via the Dickman reaction.
Okay, thank you to Nur Ayu Shafika for the question. So for next question from Nur Alia Shahira. So why does the enolate form in step 1 prefer to attack the beta carbon of the alpha beta unsaturated ketone in the Michael addition instead of any other site? This topic from Michael addition.
Yeah, for Michael addition. Yeah, because there are two sites, right? That it can be electrophilic. So the carbonyl or the double bond, right? So we can have one two and one four addition. So the same thing, right? It's more preferred. You can also form there if you want to, but it's not thermodynamically stable. So the preference is still is where you will form a um, a stable product. Okay, you try to draw and form a new CC bond at the carbonyl, and with that you would and compare the products which one would really form. So in that case, when we have your resonance hybrid, right? Your resonance hybrid, you have your carbocation at the carbonyl or the carbocation um, at the CC bond, C double bond C bond. It would always prefer to have the more stable resonance structure, resonance carbocation. And since that is the more stable resonance carbocation, then it will be the one that is preferably attacked than the other one. Okay, so we have what we call the preference due to stability. Okay, so whenever a compound attacks one compound, it would always prefer to where you have the more stable carbocation. So that's why in your what's that Dickman? No, in your Michael addition, it's always at the beta position that is being attacked. That is the more stable position of the resonance carbocation.
Okay. So that's for the answer, Michael addition. Next, from Aisha Shahila. So why is it necessary to have at least one alpha hydrogen on the ester?
Yes, it is necessary to have at least one alpha hydrogen on the ester to form your enolate. Otherwise, if you don't have an alpha hydrogen, you can no longer form an enolate, and so there's no reaction, a succeeding reaction. So yeah, at least one alpha hydrogen is the necessity. You
On
can have more, but you can't have none. Okay. But
okay.
if you have more, then you can have a lot of products. You
Yes.
have many choices.
Product,
Then
yeah.
later, you would think of which one will be the most preferred product, which one is the most thermodynamically stable, something like that. So you have a lot of considerations. But if you have at least one, you only have one choice and you only have one product.
And then next question. So why are beta diketone and alpha beta unsaturated ketone particularly suitable for the Robinson annulation? This one from
What are beta diketones and alpha beta unsaturated ketones particularly stable for the Robinson's annulation? Okay. Yeah. It's particularly suitable for Robinson's annulation to have alpha beta unsaturated ketones because the presence of resonance hybrids. Now, resonance means stability of your reacting compounds. Okay, so uh, so this is the main reason why these alpha beta unsaturated ketones are particularly suitable. And the beta diketones is the source of your enolate. Okay, so your enolate must react with your alpha beta unsaturated ketone. So they are suitable because your beta diketone has a specifically very active methylene carbon where you have your acidic hydrogen. So that is a very ready enolate. Now, that very ready enolate will readily attack your alpha beta unsaturated ketone, wherein the attack is at the 1,4 addition, meaning at the double bond, which is a more preferred position for the enolate to attack. So this good combination of your beta diketone and your alpha beta unsaturated ketone is good for Robinson annulation.
okay. So next question from Nuliana. Can Robinson annulation be performed under basic and acidic condition?
Uh-huh. Yeah. I think you should be the ones answering the questions too. Okay.
So for
Mm-hmm.
next question, Shamira Patricia. I would like to ask why does Claisen condensation require stronger base but although only can use
Use sodium hydroxide. Okay. Well, sodium hydroxide is also a strong base right now. But just aldol, simple aldol is different from Claisen now. Because Claisen undergoes what we call intramolecular, no? Intramolecular reaction. Okay. So um, in Claisen, you know, it, it's possible that no, in aldol, the alpha hydrogen has a very exposed, is very exposed, right? Because it's not in it's not a dione or dicarbonyl. But in Claisen, only one position is exposed and the other alpha hydrogens are inside. Okay, inside. So uh, the shall I how shall I frame my mind? Um, so perhaps it is easier no, to remove the hydrogen in the glycine in the aldol because of these are smaller carbonyl compounds. in Claisen, of course, we have a very large molecule, and so we should use a stronger base, but not very strong. Okay, actually, the difference between your sodium hydroxide and sodium ethoxide is not that very strong, actually, very large difference. Both can actually work, but we just prefer the sodium ethoxide for the glycine. I think, no, I think that's just because of the initial molecule where your base is reacting.
Okay, so next question. So, why do some condensation reaction form cyclic compounds while others don't?
Oh, yeah, for acyclic, nah, because in diketones or diols, your carbonyls are within a compound. So if they are within a compound, they are reacting, and so they will form cyclic structures. The other one, the other ones, they are not, your aldehyde or your ketones are not in the same compound. There are two different compounds or same compounds, like two aldehydes and two ketones. But that will give you an acyclic product. But if you have your ketones or your aldehydes within a molecule, you will simply form your cyclic compound via intramolecular. This only happens, cyclic product only happens for intramolecular interactions, okay, within the molecule.
Okay, so next, how can we determine the most acidic alpha hydrogen if multiple esters are involved?
All right. So this is actually your chapter 1 in your or chapter 3 in your basic organic chemistry, right? So there are there are many ways by which you could look at the acidity of your hydrogens via inductive effects, resonance, what else? Resonance, inductive, or just the nature of your proton, right? So, but in your diketones, for example, your methylene is very active. Your CH2 hydrogens there are very acidic because there are electron withdrawing groups. E- Electron withdrawing groups that withdraws the electrons away from the protons. So the tendency of your carbonyls is to draw the electrons away from your protons. So if the protons are deficient in electrons, they become more positive. So since they are positive, they are easily removed by a base which is negative, right? So they are electron rich. Your bases are electron rich. They abstract the proton, which becomes electron poor due to the inductive effect or the electron withdrawing group of the carbonyls. So the more carbonyls or the more electron withdrawing groups in the molecule, where your proton is situated, that proton is very acidic. Okay, so that is with this condensation reaction, that is your consideration. Which one is this acidic or this is more acidic? You have to think of inductive effect, electron withdrawing, resonance effect, those things. Okay.
Okay. So next, is there any limitation in Robinson annulation?
Oh, Robinson's annulation, the formation of six-membered ring, right?
Yeah.
Um, yeah, the limitations, of course, are if there are no enolates, no good enolates, and also, well, I cannot think of a limitation unless you will be, uh, yeah. So far, I don't know. I don't know if there are limitations for Robinson's annulation. Maybe for presence of very large molecules, which will give you steric hindrance when you form the ring, because if there are very large R groups attached next to those forming your new CC bonds, then that will give you a lot of steric hindrance. So that limits now the formation of a six-membered ring. If there are a lot of rings already and groups that will prevent the formation of new carbon-carbon bond. I think that's the limitation for the Robinson's annulation. That's why you see they the connecting compound should be free of all those steric hindrances.
Okay, so I agree with you because of a steric hindrance of the
Mm.
compound. And then next from Irfan, so why do the Dickman condensation can form both five-membered ring and six-membered ring, but for the Robinson annulation reaction only can form six-membered ring? Is it because of the stability?
Ah, in the Robinson's annulation, it forms six-membered ring because you already have the two two carbons, a carbonyl and where you have your alpha carbon. That's a portion of the carbonyl compound that is reacting. So two. Plus you have your alpha, beta, unsaturated ketone that is four. So two plus four, when you combine them, we will have six-membered rings. So it will always form the six-membered rings because of the condition of the starting materials. But for the Dickman, it can have five or six depending on your dione or your dial. If uh, that is why I told you it can also you can have seven or four, but it's not good anymore, no? But it can form or six, five or six, depending on your starting material, whether it's a six-membered or seven-membered dial or dione. Okay, so it has more preference for the Dickman, but for Robinson's annulation, only six-membered because of the two and four combination.
Okay, I think that answer for the next question. Can Robinson annulation form ring other than six-membered ring? You already answered. And then is where is alpha beta condensation commonly applied in organic synthesis or in industry? I think
Oh,
see application in industry.
yeah, in industry. I think I'm more on biochemistry now because yeah, I've not been in industry and I don't do also synthesis, but I do biochemistry. So that is synthesis within plants because I'm doing in natural products or animals. Yeah. Okay. So in biochemistry, where is that? Yung the dehydration process now, we are forming um beta hydroxy is formed first in the beta oxidation before it becomes double bond elimination product that is in before it can form you know if you have already discussed beta oxidation in your biochemistry class, that is where we can apply this alpha beta condensation. But as for industry or I don't know because I'm not doing it, I really don't know where I
But it's
can.
okay, Dr. Melvin, because my student actually from program forensic analysis.
Oh, forensics.
Analysis. That's why they ask. Maybe for future internship LOI. Okay.
Oh, yeah, organic synthesis.
Okay.
Well, Dr. Noor is doing organic synthesis, so she is applying always this alpha beta condensation.
Yeah.
But
Most
for
the
me, I'm understanding natural products via the synthetic pathway of animals, plants. This is where we apply beta condensations. How plants will form one natural products to another, elimination, condensation. This is where we apply it. Okay.
So for the next question, how does the temperature affect the outcome direction in terms of the condition? Temperature, is it
Ah, yeah.
affected direction?
Act- um, Actually, condensation reaction can happen even in ambient temperature. No, as long as you have the base, then you can condense the product. But for the dehydration process, of course, temperature is very important. Okay, you need a strong acid and heat to uh, to dehydrate, to remove the HOH component of your beta hydroxy aldehydes or ketones. That's where you will need temperature, the thermodynamic conditions. But for initial, in the inulate formation, actually they can be done even in room temperature.
Okay. So next, what causes the final Claisen product to be more acidic compared to starting ester, starting material ester? Or the final product?
Place and product. Place and product to be more acidic than the starting ester. Um, hmm. Perhaps you could answer, help me, Dr. Noor.
Maybe because of the net in mechanism, we added some source of
Mhm.
proton in the intermediate. So that's why the final product is more acidic compared to the starting material.
Oh,
That's
the
general of
okay.
the answer. Okay. So
Mhm.
for the next, I think we have two questions, two more questions. I would like to ask about what would happen if the inolate formation step is incomplete or non-selective in Robinson annulation.
Oh, if the inolate formation is incomplete, then there will be no CC bond formation. There will be no condensation process that will happen even in Aldol, Robinson, or in Dickman.
Yeah,
That's why I've been telling you the
the
formation of the inolate,
is very
an ion is the most important part of condensation reactions.
yes, correct. The inolate formation step is very important to further the final product.
Mhm.
So last question, okay, I would like to ask, can Claisen condensation occur with all esters or are there any exception?
Glycine should be diesters and other carbonyl compounds, right? You have seen a while ago that there are some that are not esters. There are um, chlorides, not ester, and then acid chloride. Okay, so it's the dione, something dicarbonyls. Now, not necessarily diesters.
But in this topic, actually we are focusing on for ester. So that's why the Claisen condensation involving the ester. Actually, it can involve
Yeah,
another
it's
function too. Yeah,
yeah, others.
yeah.
You have an ester, but the other moiety may not be fully esters. But glycine, yeah, formation, it's condensation of esters. So you have to think about that. So some exceptions, they are not they're not used. While they are possible in your drawing, it may not be possible in the laboratory. So it is possible in paper, but not possible in the laboratory, something like that. But it's it's why we call it Claisen condensation, because Claisen use the esters,
Okay.
formation of
So much,
esters.
Dr. Melfei. So informative. Since you are lecturing, your PowerPoint is so informative with the good example. And thank you so much for all the answer that you feedback to my student question. And I think maybe in future I can invite you again for sharing some research area to our
Yeah,
student. Okay, Dr. Melfei.
yeah,
Okay,
yeah. Thank
before
you.
we finish our session, I think I would like to ask my student to open your camera to take some picture. Okay,
You just send me the pictures, doctor.
Can, of course. Can. Dr. Melfei,
Thank
can you
you.
share your PowerPoint to
I share.
so I can contribute, distribute to my student? Okay.
Yes, I will give it via your email.
Yeah, yeah.
Yeah.
You
Okay.
can email me your PDF in PDF form, your slide.
Yeah.
So,
Yes.
any of you, please open your camera. At least we can see your smile, your face. Okay. Okay. Currently we have 55. Okay. Open. Please open camera. I'm still waiting you all to open your camera.
Wow. A lot of students.
Actually, my student is 66, Dr. Melfei. Maybe
Oh,
of them go for another class or they have at any location, different location. Okay.
yeah.
So please open your camera.
Some are very shy. Maybe they are in the shopping malls.
They active in chat. Yeah, still very shy. Uh,
Yeah.
it's okay. Your background from any location. As long as you open your camera. Okay. So I take the picture. Smile. Okay. Anyone want to open camera? Please open your camera. Okay. It's okay. Your background in any location. Just to take your face, your smile with Dr. Melfei. Okay, Dr. Melfei actually active in research, right, Dr. Melfei? So
Yes.
maybe any of you, if you want to do some program mobility to
Uh,
Philippines,
you can
university,
come to my research laboratory.
Santo, no, you can go and you can apply. Because I have several of my students from the previous Dr. Melfei. I send them to my collaborator to do some industry training, attachment,
Oh,
and final project. So under
that's
the
great.
mobility program, it's good for the collaborator and also for student.
Yeah.
Okay, I take a picture. Okay, smile. One, two, three. Okay, another one picture. Okay, smile. Give some peace, mini love. Okay, thank you so much.
Yeah. Thank you.
It's a very attractive collaborative teaching today.
Yeah, you can share my profile to them so that if they're interested to come to my lab, they can visit Philippines.
Sure, sure. Thank you so much, Dr. Melfei. Thank you so much for your
Okay.
kind presentation and also for your. This is actually my first time meet you through platform Google Meet. Okay,
Yes.
next time you want to visit Malaysia, so you can visit our lab in Kuala.
Yeah, I was there last year, but I wasn't able to meet Sharul. So hope to meet you soon.
Inshallah. Okay. Okay, Dr.
Yeah.
Melfei. Thank you.
Okay. Thank you. Thank you so much. Bye.
Bye, everyone. Thank you so much.
Bye, everyone.
Thank you, Doctor.
Thank you.
Thank you, Doctor.
Thank you. Most welcome.